Welcome to this video on vectors in 3 dimensions. Some of the prior knowledge includes everything about 2-dimensional vectors, including magnitude, vectors between 2 points, and equal vectors. Some of the definitions that we need to be aware of. The first one, the real coordinate space of dimension 2 is a real coordinate system in 2 dimensions. A real coordinate space of dimension 3 is a real coordinate system in 3 dimensions, adding depth to our 2 dimension. Each point will now have 3 components instead of 2, so our points will have x, y, and a z component, which is our depth. The coordinate system is drawn based on the right-hand rule. I have drawn this in 3 different orientation. In all cases, our index finger corresponds to the positive x-axis, our middle finger to the positive y-axis, and our thumb to the positive z-axis. The final drawing is the orientation that we usually use for most of the cases, x being right, y being up, and z being coming out of the page. Now let's draw our new coordinate system and let's put a point on it. Before, we just needed a rectangle to represent the x and y component of our point, but now we have 3 components, and therefore we need a rectangular prism to represent that point. If we have a vector, position vector OP, it originates at point O, which is the 0, 0, 0, and it terminates at point B, P, which has x, y, and z components. The x components, when we're drawing it, kind of originates from the ZY plane and it moves towards the point P. And we can see that on our cube, the y component of this is going to originate from the XZ plane and point up towards point P. And finally, the Z is going to originate from the XY plane and move towards P. And we can see all those 3 components of the point. And again, the position vector originates at the origin and terminates at point P. This position vector can also be written in unit vector form. We can write this as x multiplied by unit vector I, which points towards the x direction with components 1, 0, 0, y multiplied by unit vector j, which is our unit vector in the y component with components 0, 1, 0, and our new unit vector k multiplied by z, and unit vector k points in the z direction with components 0, 0, 1. The idea of writing a vector between 2 points still remains the same. So let's say we have 2 points, points A and B. A has components xa, ya, and za, and B has components xb, yb, and zb. The x component of vector AB will be xb minus xa, the y component is going to be yb minus ya, and the z component is going to be zb minus za. Those are the x, y, z components of point B minus the x, y, and z component of point A. The idea of finding the magnitude of a vector also remains similar to before. We still use the Pythagorean theorem, but now in 3 dimensions. And if you have a vector with components ax, ay, and az, its magnitude is going to be the square root of ax squared plus ay squared plus az squared. So, for example, if we have a vector A with components 3, negative 1, and 2, its magnitude is going to be the square root of 3 squared plus negative 1 squared plus 2 squared, which is going to equal to the square root of 14 units. Now the next idea is equal vectors, and for 2 vectors to be equal, they need to have the same direction and the same magnitude. So if we have 2 vectors, vector A with components ax, ay, and az, and vector B with components bx, by, and bz, for them to be equal, the x component of vector A needs to be equal to the x component of vector B, the y component of A needs to be same as y component of B, and the z component of vector A needs to be equal to the z component of vector B. Now, if you have 2 vectors that have the same magnitude and the same direction, they have to lie on the same plane. So they could either be on top of each other, being coincident, or They could be apart, but they will always lie on the same plane. The summary of this lesson is fast forwarded, so you can pause it and write down any information that you need. And now we're going to look at 2 examples. Okay, here's kind of like an application question. We want to identify the triangle that is formed between 3 points, and these 3 points are now in 3 dimensions. To figure out the type of triangle, we need to look at the length of the different side, and if we figure out that all of the sides are the same, then we got an equilateral. If 2 are the same, then we got an isosceles, and otherwise we have a scaling triangle. So we're going to find the lengths first. So to do that, first we're going to figure out the vectors. So vector AB, vector BC, and vectors AC. Vector AB is going to have components 3, -2, and 4. And then we can find its magnitude by the magnitude formula, 3 squared plus -2 squared plus 4 squared. And that's going to give us square root of 29. We're going to do the same thing for the other 2 vectors. So vector BC is going to have components -1, 6, and -1. And then we can write the magnitude equations again, and it's going to be the x component squared plus y component squared plus the z component squared, and that's 1 plus 36 plus 1, which gives us square root of 38. For our final vector AC, we're going to get its components, and it's going to be components 2, 4, 3, and if you want to find that magnitude, it's going to be the square root of 2 squared plus 4 squared plus 3 squared, and that is equivalent to 4 plus 16 plus 9, which is square root of 29. We can draw this out just to give us an idea about how it looks like. So from point A to point B, the magnitude was square root of 29. From A to C, we have root 29, and BC's magnitude is root 38. Okay, we know it's an isosceles triangle because 2 of the sides are the same, but we also want to test for a right triangle by using Pythagorean theorem. That means square root of 29 squared plus root 29 squared should equal to root 38 squared, given that it is a right triangle. Root 29 squared is 29, root 29 squared is 29, and root 38 squared is 38, and 29 plus 29 is 58, which does not equal to 38, meaning that the triangle is not a right triangle. And now we know, since we have 2 sides that have equal magnitude, those 2 sides being side AB and side AC of the triangle, then we have an isosceles triangle. For the next example, we are going to give you 3 points from a parallelogram ABCD, and based on those 3 points, we want to determine the coordinates of the last points. Okay, the first thing we're going to do with these types of questions is to actually draw it out. We have a parallelogram, so we are going to label the points A, B, C, D, and we can do this clockwise or anti-clockwise. It doesn't really matter. And based on those, we know that we have points A, B, C, and we want to find coordinates of D. We have vector BC and vector AD, which are in the same direction. So vector BC, to find it, we're going to subtract the x, y, and z components of point C by point B, and we're going to get 8, -3, and -2. And we know that vector AD is equal to vector BC because they're going in the same direction and they have the same magnitude. And we have vector BC already, and vector AD is going to be the x component of point D minus the x component of point A, y component of point D minus y component of point A, and z component of D minus z component of point A. Once we do this, we can write 3 different equations and find the 3 different components. So xd minus 2 is equal to 8. Yd minus -3 is going to equal to -3. And finally, zd minus 5 is going to equal to -2. When we solve this, we're going to get x component of point D is equal to 10, the y component of point D is equal to -6, and the z component of the point is going to equal to 3. And that's going to be our final answer. I have designed a few questions for you folks to try out so you can kind of see if you understand the concepts or not. And I will try to post the solution to these as soon as I can in a separate video. I hope that this video has helped you understand a little bit about vectors in 3 dimensions and how their operations work on them graphically and algebraically. And thank you for watching the video.